Yeah, I'm Cengiz Pehlevan. I'm an assistant professor of applied mathematics at Harvard University. So my research is in, I'm a theorist working on problems arising in neuroscience and recently machine learning. And today I'll be talking about basically deep learning theory. And my talk got longer and longer as I went through these basically sessions because there were so many things I wanted to also comment on. So we'll see how this goes. Okay. All right, perfect. Okay, so I'll jump right into this just for time's sake. So this talk is going to be about basically training a deep feed-forward neural network in a supervised manner. There's going to be a data set. So X's are going to be inputs and Y is going to be output. Even though I'm drawing multiple outputs, I'll be focusing on a scalar output just for notational simplicity today. And P is going to be my data set size or basically, and the Greek index mu is going to be that data set index. And let's assume some loss. And I'm going to be talking about gradient descent flow on this, so no stochasticity or no discrete step sizes. Okay, so the theta are the parameters, and under gradient descent, the theta evolves in time this way. So that's just gradient descent. And the first point I want to make is there's also sort of another description here, which is in the so-called function space. If you want to describe the evolution of the function that this network expresses on, let's say, a test point under this gradient flow, it's just about a chain rule. You can write it this way, right? So this delta mu being basically the gradient of the derivative of the partial derivative of the loss with respect to the function itself. And there's this object that arises here, which has a name, and it's called the neural tangent kernel. So that's going to play an important role in today's talk. Just to make sure we're on the same page, this is defined by the dot product of the network's output with its gradient with respect to the network's parameters. And it has two sort of indices corresponding to the training, so the test data, and also training data. Okay? And of course, this depends on time because it's itself is a function of the neural network itself. So it's a complicated object. Okay, so this is obviously a complicated dynamics, complex thing. How do we understand? How do we describe? So what I'll describe today is basically a good old theorist strategy of studying some non-trivial and hopefully tractable limits to gain insight. And in particular, I'll be talking about three such limits today, and one a well-established and as Haim called this uninteresting, I'll call this a less interesting limit, and two less explored but more interesting limits. Okay, and let's just jump into it. So let's look at the first limit. And this is an influential one. It has gained a lot of insight in the last years, and it's this limit of an infinite width. What do I mean by this? So these are the equations that define my neural network. In goes some x, and that goes through some nonlinearities, and there are fine transformations. I'm suppressing biases just for notational simplicity, and so on and so forth. At that point, you get the function out. And so what we're going to do is we're going to take a look at each layer, and so each of these are going to have some particular width, meaning the number of neurons in that layer, and take that to infinity. And because so that's point one. And point two, we're going to initialize this network in a random manner. So maybe we're going to choose these W's weights from a normal distribution with mean 0 and variance 1. And in that limit, because you can see some kind of a central limit theorem kind of thing is going to happen because of all these random numbers adding up. And this network is going to basically end up being described by Gaussian statistics. Okay, so one way this has been established by many people, and a lot of papers. So one consequence of that sort of simplification is the following idea. So this learning dynamics simplifies in the sense that instead of this kernel object being a function of time, it basically freezes at initialization. Okay, so you initialize your network, you calculate the kernel in that limit, and that freezes. Okay? And now, of course, our job is much simpler, especially if this losses, for example, was a mean squared loss. These deltas are going to be linear in F, so all we are left is basically a linear differential equation. We can solve it. We can try getting insight from it. Okay, so it is uninteresting for another reason, which I'm going to comment in a second. All right, but the simplification basically is in pictures is another way of saying same simplification. this network where all layers are trained becomes, or it gets replaced with, this alternative scenario where you take the input X and pass it through some static features. So this is like the kernel machine kind of an idea. And these static features are defined by, again, these gradients at initialization. And then you linearly combine them to produce an output. So all that complexity gets reduced to this basically not linear, but linearized picture where you have some nonlinear features and then training on top of this. And if you just track the equations of these gradient descent equations in this limit, you'll figure out quickly that in the limit that training time goes to infinity, the solution of this training procedure converges to the solution of a kernel machine, a kernel regressor, basically with the kernel defined by this object, the dot product object over here. So this defines a correspondence between this complex neural network in a limit and this kernel machine, which is well studied and has lots of theoretical sort of guarantees and results and so on and so forth, which you can use to gain some insight. So in particular, I'm going to talk about our work on this limit. So it's basically described in these two papers, one from ICML, I think 2020, and this is Nature Communications last year. And what we did in these two papers were basically derived a statistical mechanics theory of generalization of kernel regression. And because of this link, this theory is applicable to neural networks. So I'm not going to go through the derivations and the definitions. I'm just going to point that this theory is sort of works well. So what I'm plotting, for example, on the right is three things. So the solid line is the theory. This is our statistical mechanics theory. It's prediction about the generalization error on a three-layer neural net, basically a three-layer network with some width 800 MNIST. And the circles here are, the triangles here are the generalization error that you get from the infinite width kernel. And the error bars basically correspond to different way you can choose the training data set. So on the x-axis is the number of data that you're training with. And the circles are basically neural network experiments. This is a three-layer nonlinear neural network that you train and calculate this prediction error, and basically it's on top of it. It starts deviating after some point, and this theory is obviously not working everywhere, so it has pros and cons, and we can begin to talk about that. So on the left is another example. So this is a slightly more complicated data set, CFR10, and this is again the kernel. This is the theory, NTK regression. The reason this is not statistics exactly on top of it is because my student did not fully train basically to the subsampling of to invert. There's a kernel inversion that you need to do, but anyway. But the other point I want to make is, so this is a neural network that's trained at this depth with some width 5,000, and it's not doing very bad, this theory is. And I want to point that basically this is a theory where we actually are comparing our predictions directly to the neural network. It's not an upper bound. It's supposed to describe a typical case scenario.
Can I ask a question?
Sure.
So the y-axis on the right plot is the loss or the error?
This is the generalization loss.
Loss or the error?
Error.
So that's 10% error.
Yeah, so this is a MSE loss. It's not a classification loss. So
okay,
I'm thinking of, 0.1 basically. Cool. So the reason I'm bringing this is basically using this theory, we can get some insight about like certain things about neural networks, and to the extent that these curves fit neural networks, those results are valuable. So I'll just point to, because these were topics that came out in discussions here. So one is this idea of a spectral bias. And this is the following idea, the idea that a neural network basically fits functions or data sets with functions of increasing complexity. If you give it a few samples, it will try to fit a simple function. If you give more samples, it will try to fit a more complex function. But what defines simple? What defines complex? So in this limit, the simplicity and complexity is governed by the eigenspectrum of this kernel. You can basically diagonalize this kernel on a dataset distribution. So the dataset distribution is something you choose. And that basically gives you a bunch of eigenvalues and eigenfunctions. And the point is, the network in this limit is going to try to fit data with eigenfunctions with high eigenvalues first, and then decreasing eigenfunctions and corresponding eigenvalues. So I can talk more about this, but it's a very example that we can basically analytically work out in full detail. Suppose our data set is basically inputs are sampled from a uniform on a sphere on some high dimension. So in this particular case, it's 15 dimensions. In this case, you can show that the eigenvalues and eigenfunctions of the NTK are spherical harmonics. And suppose you want to fit a function that has basically some spherical harmonics content. So these are spherical harmonics. Now one of them is degree and one of them is order. So I always forget. So I'll say fixed k content. And you can show that basically as k gets higher and higher, so first of all, neural networks will try to fit these functions with low k functions first. And as you add more and more data, they'll try higher k spherical harmonics. And you can prove that basically in a high dimensions limit, the kth mode will be learned only after seeing d to the k samples. So if we were trying to, for example, fit a function with 7th order harmonics over here, you will need, in this particular case, about 15 to the 7 samples even before seeing any reduction in generalization error. That is what's been plotting over here. After about 15 samples, a function with only a low order harmonic gets learned. But for example, after only about 15 to the 4 samples, a function with only k to the 4th order harmonics content gets learned. So this basically tells us something about the inductive bias of these neural networks. They have preferences towards simple functions. So other point I want to talk about in this limit is something about these power law and scaling laws that was talked a lot about in these sessions. And Ethan kindly actually pointed to this paper yesterday. So in the kernel limit, you can show that if this eigenspectra is falling by a power law, and that the functions that you want to fit also have some, let's say, expansion in these eigenfunctions whose coefficients also fall like a power law, you can show that these generalization error curves should be falling like a power law. And these power laws are given by this interesting combination of these A's and B's. These are the corresponding powers. And so we had this prediction, and also Ethan and Yasaman Bahri and collaborators had an independent prediction of this law. They used our theory to get this one, but did the prediction independently, and they have also other predictions about other scenarios where you get power laws, and they really tested this in a lot of scenarios. And these are the ones that gets you powers like 0.3, 0.4, but not integers. So this is the regime. So there's a result from scaling laws in this limit. Okay, good. Of course, the problem with this limit is that there is no representation learning. So, right, because the features that are here is in a sense interpretable because they're static, but in another sense, I mean, they don't adapt to data. So that's the problem. But and the premise of deep learning is that it learns features that adapt to data. So we have to go beyond this limit. Okay, so the question is, do non-trivial but tractable limits exist for representation learning? So I'll describe two. So the first one is about from this paper. So this one is talking about neural networks as kernel learners, not a kernel machine. Basically, I'll describe a limit where the neural network's output again becomes a kernel regression solution, but not with the initial tangent kernel, but with a different kernel. And the idea goes like this. So this is, again, our training dynamics. So suppose some magic happened and someone actually gave you what this K was, okay? We have to solve it, of course, but suppose someone gave it to you. And then you realize that, okay, actually, I mean, I can write down a solution of this. It looks like this, basically. The small k and large k are basically this k, some functions of this k. I don't need to, so that let's just keep it over there. And if you stare at this equation for a while, you'll realize that, okay, suppose if the following scenario happened, you will get another kernel regression solution. This is the following. Now, this might sound like a miracle, but I'll argue that this actually happens. So if you start your network from a small initialization, so meaning that like, so we're not talking about an infinite width limit anymore. This is any width. Okay, and I'm going to choose the variance of my initial parameter small. So that sigma is basically that variance over there. And small, if given with this sigma, sorry, this is standard deviation, I believe, the initial network output and the kernel is going to scale this way. And further, assume that the kernel is small until some time tau. And up until that time tau, basically the kernel's let's say eigenstructure is evolving, and after only that, you just evolve only in scale. So that's a very big sort of assumption, but follow me for a second. If you just get these assumptions and plug in here, you will show that in this limit, the kernel again becomes a kernel machine, but not with the initial kernel, but with the final tangent kernel, which has evolved to learn features from data. Sure.
Is previous
Yes, this is all gradient flow. Yeah, I'm not sure if you did a descent version with discrete steps, probably you could do that, but I'm not sure. Okay, so I mean, this might sound like a miracle, but we showed that this happens in deep linear networks on whitened data with a mechanism we call silent alignment. So deep linear networks, we can do some analytics, and we can show all of this actually happens if you initialize small. I'm not going to go into that analytics. I'm just going to illustrate that the same thing numerically happens in some nonlinear networks. So it's just the first example. I'll show another example in a second. So for example, this is a 2-layer ReLU multi-layer perceptron. So, and the mechanism we describe is called silent alignment. What happens is the following. So this is the training loss. As you're seeing, so everything initialized small. This is the tangent kernel's magnitude. And this basically, green line is something we call alignment. Basically, it measures, let's ignore it for the moment, actually. So what happens is, in the beginning, the kernel starts small, and so this is a place where it's basically learning a lot of its eigenstructure. So this alignment actually is measuring that thing. And during that period, the loss is basically constant. And after that, the alignment or kernel's eigenstructure is more or less static, and it grows in magnitude. And during that period, the loss suddenly drops and basically comes to a sort of asymptotic state. And if you compare the neural networks, let's say, test predictions using the neural networks test on some data versus prediction using the NTK, this is initial versus final NTK, you basically find that the initial NTK is not a good descriptor anymore, but the final NTK is basically a perfect descriptor. The same thing applies to more complicated neural networks if you initialize small. So, I mean, the dynamics are not as clean. If this was a linear network, it will be even more cleaner. But you get the same conclusion. Small initialization basically leads to having a kernel regressor neural network, but the kernel is the final kernel. So since this is an Outlook session, I chose to describe these works, which are not obviously fully developed. But I mean, the nice thing about this limit is at the end, you can still describe the neural network as a kernel method, which has clean definitions of what features are and so on and so forth. And the hope is basically to be able to look into these and say something about what features have been learned. Okay, so that was the second limit. Now we're going to go to a third limit. So in the first limit, I talked basically about the trained neural network. In the second limit, I also talked about the endpoint of training. Now we want to describe something about basically the full training dynamics. Okay? And we're going to do this through basically some kind of mean field theory, some tool that's coming from physics here. And the change we're going to do is basically the following. We're again going to be considering an infinite width limit, but we're going to introduce a parameter over here. So that's the new parameter gamma. This gamma is going to go to infinity. Okay, it's going to go to infinity in a way that's basically scales with the square root of, this should have been L plus 1. Sorry about that. Or maybe this should have been L. I'm not sure. Okay. Anyway, so, and the idea is that you will show, what I'll argue is that with this kind of a scaling, the infinite width limit will again make sense in the sense that there will be some deterministic functions that describe this network's evolution. However, you will also be able to get some representation learning, meaning that kernels are going to move and the network is going to describe something. Okay, and of course, I mean, as these similar limits, these are there's a class of limits called mean field limits, and Grant in the morning commented on one, and there are other ones that consider the similar limits. So the difference of our work is basically we use this formalism of dynamical mean field theory. I'll skip all the details. But what comes out of this is basically the following. You can describe the temporal evolution of this neural network using, in this limit, some dynamical objects, which are also deterministic in the sense that they are independent of the network's initialization in that limit. And these are basically feature kernels. And these are, I mean, Haim in the morning talked about this in the context of his theory. And these are basically, this has indices of layer and basically pairs of training data points, and also time indices. These are dynamic now. We're describing temporal evolution of these kernels. And then also the gradient kernels. So these are basically gradients that a particular layer sees with respect, at a particular layer with respect to a particular pairs of data points. And what these quantities do is they describe non-Gaussian processes over which hidden layer activations and pre-gradients evolve. And there's a bunch of equations which I'll skip. I'll just point that, it turns out, there's a parallel work by Greg Yang and who which derived the same exact stochastic process using their tensor programs thing. And I'll just show you some results about this. So this is the training loss dynamics over time. This is the NTK limit when this parameter gamma is 0. And this is the a particular value where basically you're in a representation learning case. And the DMFT is basically fitting all these dynamics very well. Also, the DMFT is fitting all the histograms of hidden layer activations and pre-activation densities very well. And also, it's describing kernels very well. So what you're seeing here is basically the layer kernels that's observed in training dynamics of a neural network. And this one is basically the one that you would get from theory, their temporal evolution, and all that kind of thing. So I'll just comment on 2 slides and I'm done. Okay, so what you see is basically, as you go more and more sort of representation learning, let's say, the distributions of these hidden layer activations become less and less Gaussian. But the DMFT is able to capture these deviations. And the final thing I'll comment is this was a comment about, there was talk about some approximation schemes. So here I'm plotting various approximations that have been considered in literature about basically when considering deviations from infinite width limit, for example, well, the NTK being infinite width limit, there's a perturbation theory, there's some assumption about gradient descent. And they all work well in some regimes, but the DMFT is basically able to capture the full dynamics. And these are, again, comparing different approximation schemes and how well they capture evolved kernels. Okay, so I'll finish by saying, so what do you want from a theory of deep learning? So here's a wish list. These are the things I heard here. Domain relevance, meaning everybody is using deep learning for a different thing, so perhaps the questions that people want to ask about deep learning are different depending on the domain. We probably want it to be, we want it to be analytically tractable and efficiently computable. It should predict something about accurate network performance and other domain-relevant quantities in realistic situations. And it should be, I think, mechanistically interpretable through a reduced description, hopefully involving a small number of quantities and others. I don't think we are there yet, but I guess the hope is we'll get there. With that, I want to acknowledge my students who did the work, and finally also advertise the KRTP program is basically focused on exactly this point, deep learning from a scientific perspective, organized by myself, Chaim Sompolinsky, and Yasemin Bahri, which will be announced soon. And it's going to be mainly focusing on neuroscience and cognitive science, but we're open to other scientific questions and perspectives on deep learning as well. Thank you, and apologies for going over.
Thank you, Cengiz. Questions? Krastan has a question.
Yeah, I have a kind of, so you mentioned physics. So in physics, what's called DMFT is at least the one that Gabi Cutler introduced, corresponds to the self-energy of a single particle. Green's function has no momentum dependence.
Yeah.
That's what DMFT is, at least in physics. Is that something that...
Yeah, so here I'm using it in the following context. So I'm thinking of a neural network. In each layer you have many neurons. So I'm thinking, instead of describing all of these neurons separately, I'm thinking of basically describing the distribution of all these neurons coming from a stochastic process, which is basically a mean field description.
Because in physics it has a very well defined name for 30 years now.
This is the same, I think, concept.
No, but you don't have self-energies here. You don't have momentum dependencies.
There is no concept of momentum in this.
So in that sense, it's, okay. Because there the self-energy just depends on the frequency, not on the momentum. This is what DMFT is.
So there isn't a Hamiltonian here or any kind of thing, but the concept of a mean field still exists. The other thing I want to say is it's dynamical because that's coming from the following fact that we're describing temporal evolution of, I don't know if Chaim wants to comment. I mean, a lot of these methods we learned from Chaim also, but yeah. Yes, please.
So in the statement, I just want to be clear, I just wanted you to clarify the actual formal statement in the first limit that you considered that wasn't the NTK. So you have this K infinity, right?
Yeah.
So within the mean field global convergence theorems, we need to assume, you know, the existence of a convergence point. So are you saying that you can prove that you converge to a K infinity?
Yeah, so there's no mean field here. There's no.
Yeah, you know, I
infinity
understand,
here.
but
Yeah,
you know,
so
the
I'm
existence of a K infinity,
Yeah, exactly.
I think is.
So the first point I'm making is, if these three things are true, just this is true, exists. Now, are these three things true? And I did not show you, but in deep linear networks under gradient flow, multi-layer, these are true. And for nonlinear networks, I just showed you some basically simulations.
Okay, and then the other question that I have about it is that, so, I mean, is it clear that this map is necessarily contractive at all times? Because, again, in the over-parameterized limit, what can happen is that you can have a collapse of the spectrum, and, you know, you could potentially, like the Wasserstein gradient flow could get stuck, right? So that can't happen here, and is that why the data whitening is necessary, or what is the...
Data whitening, is an important concept. So again, statement is, if you're in deep linear networks with whitened data, you can actually analytically write down the solutions to these equations and show that this happens. And the data whitening is important because it might be related to your point. I have to think a bit more deeply about this. It allows the kernel's eigenspectrum to align with the data eigendirections, and therefore basically allows I'll say, like a flow on that space. So perhaps if there was no whitening, maybe something like what you're describing might happen, but I'm not sure.
Okay, thanks.
But the other thing I should say is basically for a lot of real data, it turns out, I mean, this is not a big constraint. You could remove that, and numericals will also work.
Okay, thanks. So